I'm really excited to be here. During my postdoc time here, this was my church. I'd come to the energy seminar once a week and pray to the God of thermodynamics. And it's pretty exciting to be on this side of the stage. Hopefully I don't say anything too blasphemous. So this work, evaluating flexible power grid resources, storage and gas turbines, will be a work of net energy analysis. And I did it under my advisor, Professor Sally Benson, and with my fellow postdoc in ARMS, who's now at Clemson University, Mick Carver-Hollisdale, and my friend and colleague, Professor Adam Brandt. All right, so I don't need to explain to anybody in this crowd why we need to transition from fossil fuels to renewables, but I will comment on the fact that it'll take a long time. We've been at it for about 35 years now, and if historical energy transitions are any guide, we have about another 35 years to go. And this will present a host of new challenges because instead of having piles of hydrocarbon that we can pull out of the ground and store up and burn at our leisure, we now need to tap into intermittent flows of energy to deliver energy to society. And this is what intermittent flows look like. These sort of plots are cliche at this point, but cliches are still very informative. And this is my own take on it. So I plotted 30 days of wind generation in blue, solar installation in gold, and power demand for Portland in red. So this data was taken from the Bonneville Power Administration in Oregon. And as you can see, there's a high degree of anti-correlation between power supply in yellow and blue and power demand in red. This presents a challenge to operating the power grid. So this is a photograph of the California Independent Systems Operator. And as you can see, it's highly sophisticated. It looks like a James Bond movie. These facilities are military secure, and I'm sure you need to pass a drug test to sit at one of those desks. So this is very economically sensitive work, and having these intermittent flows of renewable resources will present its own challenges to main power grid operation. Now, power grid operation is critical to, of course, the economy and machines that are operating in industry. So necessarily, the power grid will need to become more flexible. There are several different ways that we can introduce flexibility on the power grid. This is a cartoon plot. It's qualitative, it's adapted from Professor Mark O'Malley at University of Dublin. And it shows cost on the y-axis and grid readiness on the x-axis. So today we use things like power forecasting and price responsive loads. So if the power price is right, different loads will turn on or off. And we also have some demand response for high power demand industries. If those flexible options aren't available, then we use natural gas single cycle combustion turbines, or so-called peaker plants. So on a particularly hot day in San Diego, they fire up one of their 6 or all of their 6 peaker plants to accommodate the AC load that's on the power grid. There is some storage on the power grid today. 99% of it is pumped hydroelectric storage. And it has increased costs, and it is not enough to supplement all the flexibility needs of the grid today. Something new that's happening as renewables become more present on the grid, as wind energy in particular proliferates, is resource curtailment. And so curtailment of wind resources is simply feathering the wind turbine, turning it 90 degrees to the wind during times of overgeneration. And that obviously is an economic loss on whoever owns that wind turbine. Finally, under current development and at high cost is energy storage. Now these costs continue to go down, but it is the most expensive flexible grid resource today. So that's all I'm going to say about dollars and cents. The rest of the talk is kilograms and joules. I'm going to talk about how do these technologies for grid flexibility compare on an energetic and carbon basis. Here's the agenda. So I'm going to introduce the concept of net energy analysis, talk about the question of should we store these resources or curtail them from an energetic perspective. And then I'm going to compare the energetic and carbon performance of energy storage to natural gas peaker plants. And finally, I'll talk about some of the implications of this work. All right, so what is the function of the energy industry? There was a net energy analysis workshop here at Stanford last spring, and the 40 of us or so in the room came up with somewhat of an operating definition. So we state that fundamentally the energy industry takes labor, capital, and energy inputs and consumes them in an effort to deliver usable energy to society. A functioning energy industry delivers more energy to society than it consumes. So that was a bit of a mouthful. What does it mean? Biology provides a pretty useful analogy. An Arctic fox better consume more calories from a bunny that she chases down in the snow than she spent running that bunny down. Otherwise, she's going to starve. So similarly, society must generate more energy than it consumes trying to acquire that energy, or it in turn will starve. Another analogy, net energy is analogous to profit. So let's unpack that analogy a little bit. So you need to invest money to make money. To be profitable, you need to make more money than you invest. It's all pretty basic stuff, right? Investments with high rates of return are better than investments with lower rates of return. And investments that are more profitable have shorter break-even times and are easier to grow quickly. We can apply these ideas to energy systems. So it takes energy to make, operate, and decommission devices and systems needed to produce energy. And for a device or system to be useful to the global energy supply, the energy outputs from that device or resource must be greater than the total energy inputs. If that's the case, then there's net energy available to society. It can be used for discretionary purposes like a Taylor Swift concert, or it could be also used to generate more energy and build more windmills, wind turbines. So it's important to keep track of these net energy metrics. It can also be really useful for making policy decisions. So with respect to energy storage, we can estimate the energy costs and the carbon costs of energy storage. We can also compare these costs to existing sources of grid flexibility, like natural gas combustion turbines. And we can make some early technology appraisals. We can look at the characteristics of storage from an energy perspective and decide which of these characteristics make a good storage technology, again, from an energy perspective. Now, net energy analysis, in a sense, came before life cycle assessment in the early 70s, but then life cycle assessment really took off, and now net energy analysis is a subset of life cycle assessment. And so I use a lot of the same tools and methodologies that are used in life cycle assessment for net energy analysis. So these methodological constructs include looking at the energy costs in the upstream phase when you're mining the raw resources, delivering to a factory, making widgets, assembling them into some device or technology, and shipping them to their point of use. The operational phase, how much energy is consumed during the operation of these devices and technologies. And finally, the downstream phase, how much energy does it take to decommission or recycle these different technologies and devices. These pictures represent that the energy intensity of renewables, most all the costs are in the upstream phase. For fossil fuels, most all the costs are in the operational phase. All right, so here is a schematic of one of the most commonly used metrics in net energy analysis, the energy return on energy investment, or so-called EROI. EROI is the sum of energy outputs compared to the cumulative energy demand. So what's cumulative energy demand? It's all those energy costs in those three phases. So the energy associated with construction, so this is power, gigajoules per year. So anything below that y-intercept are energy costs. The energy associated with operation and the energy associated with decommission. That's going to be on the denominator of that EROI metric. On the numerator will be all the energy generated. So all the energy output from a device or resource divided by all the energy inputs. If that number is greater than 1, it's providing net energy to society. If it's less than 1, then it needs to be subsidized by some other energy infrastructure because it's actually a drain on societal energy stores. Here are a couple EROI values for renewable resources. Now these are actually an electrical energy equivalent, so how much electrical energy is delivered to society for every electrical energy unit that society pays for that resource. So something like wafer PV, it's actually better than this today. It's around 13, because these technologies are evolving rapidly. So for every unit of electrical energy that society pays to build a solar PV, that solar PV over its entire lifetime will deliver 8 units back to society. So it's a great energy resource for society. You're getting an 8-to-1 return. Wind is about an order of magnitude greater. You get an 86-to-1 return for onshore wind. So that's a little bit on net energy analysis. You can check out all the videos from the workshop last spring if you want to learn more. This talk's going to be about flexible grid resources, namely energy storage. Storage isn't a new thing to human society. We've been doing it for thousands of years. Here's an Anasazi granary in Glen Canyon, Utah. But things are a little bit more complicated now. We're storing electrons with sophisticated battery technologies and grid technologies. So what makes a good grid storage technology? First off, it needs to be safe. If we're storing an hour or up to 6 hours of energy for a town or a city or even a region, then you have bomb quantities of energy, right? So you can't have people being hurt by that. So they need to first and foremost be safe. They also need to be affordable so that they can grow and scale. They need to be made from abundant materials. You may have some killer technology, but if it requires some rare earth element that can only be found in Shangri-La, then it's not going to scale, and it's not going to be available for the power grid. They need to be robust and durable. They can't just wear out, so they need to have a high number of charge-discharge cycles, cycle life in the battery terminology. And they can't be wasting energy, so they need to have a high round-trip efficiency. That means they need to get most of the energy back out that you actually put into the battery. So technologies that satisfy most, if not all of those criteria include lithium-ion batteries, traditional lead-acid batteries, sodium-sulfur batteries, 2 flow battery designs, zinc bromide and vanadium redox, and 2 geologic storage technologies, compressed air energy storage, which takes advantage of massive hollowed-out salt domes, and pumped hydroelectric storage, which again is 99% of the power grid today. But it costs energy to build these devices, right? You have to mine the raw materials. So this is a coltan mine requiring cobalt for a lithium-ion battery in the Democratic Republic of Congo. Those raw resources need to be shipped to some factory. This is the GM Volt factory in Detroit that's making lithium-ion batteries. So there's energy consumed in producing the materials and in manufacturing these storage devices. Here's a plot of embodied energy requirements for different storage technologies per unit capacity. So to store 1 megawatt hour of energy, you need this many megawatt hours of energy to build that storage capacity. Significantly lower for these geologic storage technologies, and that's because a hole in the ground is a relatively energetically cheap technology compared to assembling complex chemistries and enclosing them in some man-made manufactured device. The least expensive from an energetic perspective, battery technology is traditional lead-acid batteries. That's because we've gotten really good at mining lead and refining lead. That's not the only thing that goes into an energy analysis of energy storage. We also need to be concerned with the dynamic effects of operating the battery. These include how much energy is lost with each round-trip charge-discharge cycle. So this is energy efficiency of the battery. How long the battery lasts, how robust it is. So that's cycle life. There's actually 3 columns here for cycle life, and that's because cycle life is depth of discharge dependent. So how deeply do you drain the battery? In general, the more deeply you drain a battery, the more secondary and tertiary chemistry reactions will occur in that cell, and these can be damaging to the cell, shorting it out and limiting its lifetime. So in this analysis, I did what I could to favor batteries as much as possible and selected a combination of depth of discharge and cycle life that optimized their energy throughput. So what's energy throughput? Energy throughput is the total amount of energy, so cycle life times depth of discharge, stored over the battery over its entire lifetime divided by its energy costs. So this is analogous to EROI, but except it's for storage, so the energy stored on energy invested. So you can see geologic storage technologies like compressed air energy storage and pumped hydro storage have much higher energy throughput values. And again, not only is the whole a energetically cheap technology, it's also a very robust technology. It doesn't really wear out. You don't have secondary chemistry reactions happening. The highest energy throughput battery technology is lithium-ion batteries. This is due to a combination of high cycle life and high efficiency. Even though lead-acid batteries have a very high efficiency, they have a terribly poor cycle life. I have read papers of aqueous-based chemistries produced right here at Stanford that are showing incredibly promising cycle life. So this is an area to watch. These lead-acid batteries may be up in this region shortly. All right. So now that we know a little bit about the energetic performance of battery technologies, we should ask, should we store or curtail renewable resources? So curtailment feels bad, right? You're just throwing that energy away. You built this nice, pretty wind turbine, and now somebody's telling you we don't need that power, throw away 10% of it, throw away 20% of it. It feels bad. It's an immediate loss. So psychologically, you just see that candy being taken away from you. But it actually takes energy to build these batteries, right? They have their own energy cost too. It's indirect and amortized over the lifetime of that battery, but we can compare that energy cost of the battery to the energy losses of curtailment. So present day curtailment rates are around somewhere between 0 and 10% in Texas and around 1% in Oregon. I hear anecdotal evidence of much higher curtailment rates in China, but nothing that I can cite. And these curtailment rates will reduce the energy return on energy invested of these renewable resources, because solar has an EROI of 8, for example, and if you throw away half of that energy return through curtailment, then its EROI will be 4, for example. So here's a schematic of that. Some fraction phi is curtailed, and the actual energy returns will be the EROI of that resource multiplied by 1 minus phi. So again, here are the EROI for solar is around 8 during the time of this analysis, and 86 for onshore wind. I need to bring up at this point another net energy analysis metric, energy intensity. It's the inverse of EROI. So to deliver 1 kilowatt hour or 1 unit of energy to society, society must pay some unit of energy. So it better be less than 1 for a functioning societal energy system. I have to introduce it because it makes the math easier. All right, so again, energy intensity is all the energy inputs divided by the energy outputs of an energy device or energy system. Calculating the energy intensity of stored renewables is a little bit more complicated, so let me try to walk you through it. Here's the energy intensity of a renewable resource, and it produces 1 unit of energy for society. That can be partitioned. A fraction of it, phi, can be stored, but now we need to pay energy for stored, the embodied energy of that storage. So that's what this energy intensity of the storage is. And that's going to be modulated by how much energy needs to be stored. So I only size it to exactly how much energy would actually be needed to build that battery. So again, that's favorable towards battery technologies. And then it's also sized by the efficiency of the battery. The energy outputs will be whatever did not go into storage, 1 minus phi, plus whatever came out of storage. And so not all the energy that goes into storage will come out of storage due to its inefficiency. So eta phi comes out, whereas phi goes in. So we get an energy intensity of this hypothetical power grid of all these energy costs, energy inputs, divided by all these energy outputs. Similarly, for curtailment, the energy intensity of curtailment is the energy intensity of the resource. That's the energy inputs, and then the energy outputs is simply 1 minus phi. So we can compare these two values and make a calculation. Is it better to store or curtail these resources? So this plot is for solar. Starts off with an EROI of 8 in this upper corner as a function of phi, how much goes through storage or how much is curtailed. So if 0% is curtailed, then it has an EROI of 8, right? It just goes straight to the power grid. If half of it is curtailed, then it has an EROI of 4, because half of that energy return got thrown away. So that line defines the EROI of curtailment. If it falls below that line, then it's energetically favorable to curtail the resource. If we fall above that line, it's energetically favorable to store that resource. So here's pumped hydroelectric. It has a negligible effect on EROI. Even if we store it at 100%, the EROI drops to about 7. And in fact, it's energetically favorable to store solar energy with all the battery technologies that I analyzed here, except for lead-acid batteries at curtailment rates that we find on the power grid today. And that's because even though lead-acid batteries are energetically cheap and highly efficient, they're very short-lived. So you have to pay the cost over and over again to maintain your fleet of lead-acid batteries. Unfortunately, they're also economically or financially inexpensive. And so Germany currently is choosing to store solar energy with lead-acid batteries. From an energy perspective, it probably makes sense to curtail that resource. Picture is different for wind, and that's because wind has a very high EROI. Or stated differently, it's very energetically cheap. It doesn't hurt that much to throw wind energy away, or to throw energy away costs less energy than to build these energy-intensive devices, these storage devices. So storing wind with geologic storage technologies, pumped hydro and compressed air, makes energetic sense. Curtailing it rather than storing it with electrochemical chemistries makes sense, again, from an energy perspective. The best one is lithium-ion batteries. Okay. But that's just the energy picture, right? We certainly care about carbon. I would almost argue that we have an excess of energy in society today, so carbon's the real problem. So let's look at the carbon intensity of these different flexible grid resources and options. Right, so here are the life cycle storage CO2 equivalent emissions per megawatt hour of energy storage capacity for these different technologies. These results I obtained from a handful of different studies. So lead-acid batteries is the most carbon-intensive battery per megawatt hour, followed by compressed air energy storage. Now this is interesting, right? Because compressed air energy storage didn't have a very high energetic cost, but it has this really high carbon cost. And that's because in the operation of a compressed air energy storage plant, you need to combust natural gas. And that's because you use electricity to compress air in a massive hollowed out salt dome underground. And then when it's being discharged, the temperature drops significantly due to the ideal gas law, PV equals nRT. The pressure is going down, so the temperature goes down as well. And it's spinning a turbine to generate electricity. And if the temperature drops down too far, you'll get ice on your turbine blades and your plant will break. And so natural gas is combusted to maintain operating temperatures. Now some energy is harvested from that natural gas as well, but it does produce significant amounts of life cycle carbon emissions. Pumped hydroelectric storage has the lowest life cycle carbon emissions of any storage technology. But that's not the only carbon effect when you store electrons. You also have to consider the carbon intensity of whatever resource you use to charge that storage device. So if you're charging it with a coal plant or a solar panel, whatever, that device has a life cycle carbon footprint. And if you want to deliver 1 megawatt hour, 1 kilowatt hour to a power grid from storage, you need to put more than 1 kilowatt hour into the storage device because of its inefficiencies. And so the carbon intensity of whatever resource you're charging that storage with is going to increase by at least a factor of 1 over the efficiency of that storage. And so it has something I call a source carbon multiplier effect, which is simply 1 over the efficiency. So for lead acid, it has an efficiency of about 90%. But it'll increase the carbon intensity of whatever resource you charged it with by a factor of 11%. Again, compressed air energy is this weird thing because you get this energetic benefit from the natural gas and from combusting the natural gas. And so its source carbon multiplier effect is actually less than 1. What that means is it makes clean energy dirty and dirty energy clean. Okay. All right, so what about the resource carbon intensity? We just talked about the storage carbon intensity. Thankfully, National Renewable Energy Laboratory has produced these excellent harmonization studies, and so this analysis has been done for me already. So for solar PV, the life cycle carbon intensity for solar PV is around 39 to 49 kilograms CO2 equivalent per megawatt hour of electricity delivered to the power grid. Most of this is associated in the upstream, purifying the silicon, that sort of thing. For wind turbines, it's very low, 3 to 45 kilograms of CO2 per megawatt hour. Again, most of it all associated with building the turbine. There's not much carbon associated with operating the device. Different story for natural gas, right? Here, the energy is actually coming from reacting carbon with oxygen and making CO2. That's where the energy comes from, and so it's going to produce a lot of CO2. 420 to 670 kilograms of CO2 equivalent per megawatt hour, and all of it associated with the operational phase. So we know the storage carbon intensity, we know the resource carbon intensity. Let's look at a few different flexible generation pathways to provide flexibility for the power grid. We can store renewable electrons, deliver them to the power grid. We can choose to store grid electrons, deliver it back to the power grid. And we can use what we use today, natural gas peaker plants, to provide flexibility on the power grid when it's needed. Now this whole talk thus far has been a look at the methodology for these analyses, but I'll just state it clearly here. So those of us that worked on it, we developed a theoretical framework to combine the energetic costs and carbon intensities of electricity generation resources and electrical energy storage technologies. We use net energy analysis and life cycle assessment to track energy expenditures and flows, as well as carbon emissions for these energy resources and storage technologies. We obtained data from several sources, but these are emerging technologies, and so the data is not widely available. This is something I want to work on in the future, get better data straight from industry. As best we could, we harmonized this data to cradle to gate. If you're a life cycle assessment practitioner, you'll understand what that means. But these data are uncertain. That being said, the work focused on building the theoretical framework. I think it's sound. I'd like to think it's sound. And so as the data gets better and better, we can use this framework to further appraise these early technologies. Just to repraise some of the math, we looked at the energy intensity, so the energy inputs divided by the energy outputs from storage, and the carbon intensity. So this is CO2 equivalent. This is the life cycle carbon emissions of the storage technology over its entire lifetime, required to deliver 1 kilowatt hour of electricity to the power grid. So this is modulated or divided by how long it lives, because if it lasts a really long time, then each time it delivers energy to the power grid, its life cycle emissions will be divided by that cycle life. But if it has a shallow depth of discharge, that will be a number less than 1 and will increase those per unit of energy delivered carbon emissions. This will be added to the operational CO2 emissions from the storage technology. This only really matters for compressed air energy storage when you're combusting that natural gas. All the other storage technologies have operational greenhouse gas emissions of 0. And then finally added to the resource carbon emission or carbon intensity, whatever charge the device, again divided by the efficiency of the storage, the so-called source carbon multiplier effect. If you're still awake and paying attention, you'll notice I haven't talked about the energy intensity or the ERI of gas yet. These analyses are still under work, but it has an EROI somewhere between 15 and 20, or an energy intensity between solar and wind. Okay. So, what's it all mean? This is the whole point of the talk. This is the carbon intensity and the energy intensity of flexible grid resources for the power grid. In life cycle speak, my functional unit is a kilowatt hour of energy delivered to the power grid, and I have 2 indicators: kilograms of CO2 equivalent per kilowatt hour and kilowatt hours of societal energy per kilowatt hour of energy delivered. To orient ourselves, I've plotted the US grid average. It has a carbon intensity of about 550 kilograms per megawatt hour, or 0.55 kilograms per kilowatt hour, and an energy intensity of 0.056, or an EROI between 18 and 20. This divides this plot into 4 quadrants. So if we're down here in the lower left, these are grid flexibility technologies that we should do today. It'll have lower carbon emissions and lower energy intensity than the US grid average. So lower numbers are better. If we're up here in the opposite quadrant, then these are technologies we should avoid. You'll be spitting more carbon into the atmosphere at greater societal energy costs than the US power grid average. This is a really interesting quadrant. Here we're trading societal energy costs for lower carbon. Again, I feel like we have plenty of energy today, so trading energy for carbon, I think, is a noble pursuit and something we should do. This is a strange area that doesn't really exist on this plot, so let's not talk about it. Okay, so wind looks like a dream, right? This is wind direct to the grid, very low carbon, very low energy costs. Even at curtailment rates of 10% and 30%, it's still producing less carbon than storing that wind in pumped hydro storage. But even with storing it with electrochemical storage technologies like lithium-ion, you're producing far less carbon than the power grid at less societal energy cost. Vanadium redox batteries, due to their very long cycle life, charge-discharge cycle life, also have very low carbon intensities. So stored wind energy looks great. You can even store it with lead-acid batteries and have less carbon than the US power grid, but you're really doing quite a disservice to wind, right? Like, that's embarrassing. Storing solar energy trades societal energy for lower carbon. Again, something we should do. So this is PV direct to the grid. Curtailing it at 10% is slightly better than pumped hydro, but as soon as you get up to curtailment rates of 30%, you should be storing that solar PV with pumped hydro if carbon and energy intensity minimization is your goal. Battery technologies all look pretty good, except for compressed air energy storage because of its combustion of carbon during its operation, and lead acid batteries due to its very low cycle life. Storing grid electrons in these different technologies in general is a bad idea. You're increasing the carbon intensity and the energy intensity of these grid electrons. Storing it with lead acid batteries is a terrible idea. I understand that this has been done in California and Germany, and there were noble intentions, but now that this information is becoming out there, I'd like it to stop because it's cringy. What about flexible gas generation? So here's a simple cycle natural gas combustion turbine here. It's slightly more carbon intensive and energy intensive than pumped hydro storage. So use pumped hydro storage if you're storing grid electrons. Otherwise, use natural gas combustion turbines. NGCC isn't entirely flexible, but it falls below the US power grid average. That's because it's slightly more efficient than the power grid and uses gas, not coal. NGCC with CCS is interesting because it isn't flexible, but my co-authors and I have talked about the possibility of using NGCC and CCS in a swing mode where you turn on and off the carbon capture and provide some flexibility in that way by changing the efficiency of the power plant. That technology isn't there yet, though. So if you blur your eyes and draw minimum area curves around these different technology storage pairings, then we can see that wind reduces carbon intensity and energy intensity relative to the power grid. Solar trades energy for carbon. Storing grid electrons is a bad idea. And gas generation is on par with the power grid, and that makes sense because of the significant presence of gas generation on the power grid anyway today. What's interesting, though, is as the power grid reduces its carbon intensity, so this is the US average at 0.55. California has a carbon intensity of 0.29, so almost a factor of 2 less. And so that's down here somewhere. So as that carbon intensity is reduced, that will pull all these storage technologies down with it. So as the grid gets cleaner and cleaner with more renewables on the power grid, then storing grid electrons will look far favorable to natural gas combustion turbines. So that's a dynamic effect that isn't included in this plot, but something that we should all be aware of. Okay, so the big ideas from this talk. Flexible power grid technologies will affect the carbon and energy intensity of the power grid. They will change the way the grid operates and how much carbon it will emit into the atmosphere. The energy resource predominates the energy and carbon intensities of stored energy. That makes sense. It becomes intuitive once you think about it, because if you're storing good, clean, low carbon electrons, then you will emit good, clean, low carbon electrons from that storage technology. Or another way to put it, garbage in, garbage out, right? If you're storing coal, you're going to get even worse, higher carbon intensity coal electrons out. These technological solutions not only need to be affordable like lead acid batteries, but they need to be aligned with the principles of environmental stewardship that guided the policy actions that put storage bills, for example, in California in place in the first place. Now this is pretty academic, but I have a few outstanding questions. I want better data. I want better life cycle indicator data. We can do this in a couple ways: input-output analyses, or better yet, get the data straight from the source from industry. Some more specific points I'd like to make. We should be storing energy with efficient and long-lived technologies, so battery R&D should focus on improving battery cycle life and efficiency. We should consider curtailing wind resources before we store it during times of oversupply. Even though it feels bad, it actually makes energetic and carbon sense. We should actually store solar, because here we're trading energy for carbon. If we are going to use peaker plants, use the most state-of-the-art aeroderivative peaker plants. Don't use old, low-efficiency peaker plants. Avoid storing grid power, and certainly avoid lead-acid energy storage. Finally, I'd like to close with one final point. I'm often accused of being a naysayer to storage. I'm not saying that at all. We should not abandon storage. We should continue to perfect it, use these net energy metrics like cycle life and efficiency to make the best storage possible. So I'd like to close with a quote from one of my favorite contemporary physicists, Freeman Dyson, who wrote all the way back in 1975 an essay called The Cost of Saying No. So it is not enough to count the hidden costs of saying yes to new enterprises. So that's what I did, right? There's these two hidden costs I counted, energy and carbon. We must also learn to count the hidden costs of saying no. It often happens in technological development that one design turns out to be not merely better, but enormously better than its competitors for reasons that it could not have been predicted in advance. So there's no way to find out the best design except to try out as many designs as possible and discard the failures. So hopefully I've discarded a few failures and provided some insight into what makes good storage in this talk. I'll close with this plot, and I'm happy to take questions. Thank you. Yeah.
So these ERI metrics don't really take into account reliability, it seems?
No, they are time independent.
Right, so I'm wondering, and this happens with LCOE things for carbon technologies, such as solar and wind. So how do you take into account, or how would these change if you had to meet grid reliability constraints with solar and wind, batteries, and things like that?
You'd have to confine the analysis to whatever time domain you were interested in. So if you wanted frequency regulation or ancillary services, for example, then you'd have to make that a condition or criteria for the storage you included. So my criteria was bulk energy storage. So my criteria were things like safety and affordability. You'd have to put another layer on there that would exclude some other technologies. Let's keep it with the students. Yeah, you in the red.
Yeah, thank you for the very interesting talk. I was wondering how you calculate where's the difference between storage for wind and storage for grid and storage for solar, since basically they're all connected.
Right. So once an electron's on the grid, you can't tell one apart from the other, right? They all have 10 to the 19, negative 19 eV or whatever. So this maps out an envelope of the grid. So I'm saying the actual power grid will be some blend of all of this. But this is one extreme here. Stored lead acid batteries is another extreme out there. And so, yeah, you cannot decide which electrons to store, but perhaps flip the storage on, charging storage, when you see a preponderance of wind on the power grid. If your power grid is dominated by baseload coal, maybe not turn the storage on, even if that's the most affordable point to turn the storage on. Yeah. Sure.
So I have a question about your definition originally. The grid, sort of like sewer and water, is supposed to be on when you go home. And you want to flush the toilet, it's not going to have a 30% chance of working. Okay. Right? So your definition really needs to encompass the fact that what the grid provides is 0.999 reliability for power. And unless you can do that efficiently, all these metrics don't really amount to much, because it's a common good. The grid is a common good, just like clean water.
Yeah, I think that's far beyond the scope of this analysis.
Well, but you're missing a point, is if you're burning gas to make the wind work or the solar work.
There are many places on the planet that would be fine with 0.8% reliability. Yeah.
So do you think it's statistically significant to include the delta because of transmission distribution technology? So let's say when you have a hydropower plant, you're transmitting 2 electrons versus like you distributing lead acid batteries over the transport sector and then.
Absolutely, yeah. So things it did not include are line losses, inverter losses, things of that nature. And so this is in a way almost a best case scenario. I could punt and say that these line losses might be similar for all these different technologies on a broad scale grid. Yeah, so you just have to basically divide again by those line loss efficiencies to increase the carbon and energy intensity. Yes?
One question about the line loss. How much does it really matter? I'm thinking about the example of Denmark. Denmark basically stores the wind energy in Norway. Does it move the point a little bit or a lot?
Yeah, I mean, this is something I'm really curious a lot. When I read about line losses, I see a value often stated as 7% per 1,000 kilometers. So I'll let you do the math. I'm tired. Yeah.
Would you explain this a little bit further? As an example, I see VRB, vanadium,
Yes.
3 different places on this curve. Why,
Sure.
Why is that?
Let me back it up and get rid of these areas. That's a really good question. So
There's your vanadium.
this legend is the resource charging storage. So blue is wind charge storage, yellow is PV charge storage, black is grid electron charge storage. And so VRB here is the energy and carbon performance of wind energy being stored by a vanadium redox battery. And we can compare that to the energy and carbon performance of PV energy being stored by a vanadium redox battery. Finally, we can compare that to grid electrons being stored by a vanadium redox battery. And the reason they're in different places is these 3 different resources have very different carbon and energy intensities. It costs different amounts of for society to produce an electron of wind energy than it costs to produce an electron of PV energy. And the carbon intensity of a grid electron is very different than the carbon intensity of a PV. And so this goes to the point that whatever resource you're charging storage with has a significant impact on the overall system's carbon intensity of electrons being discharged from storage. Did that help?
Barely.
Okay.
Help me.
Yeah, you in the far back.
Hi, great talk, thanks so much. Now, correct me if I'm wrong, I'm trying to figure out, so where would nuclear fall on this graph? So it'd be basically zero, I like to laugh, thanks.
Yeah, no.
So it's basically zero carbon, electrical energy intensity, I think is probably around wind without storage. And how does that fit in with future nuclear technologies coming up?
Yeah, so ERI analysis on nuclear energy hasn't been done for quite some time. Most of the values I see are stated from the 70s, and it's unclear whether they're doing primary energy investment values or electrical energy equivalents. The values I do see are around 10. Again, I don't know if that's primary or electrical. If it's primary, then electrical would be down to 3 or something, because you'd have to divide by the efficiency of the grid. But I'm starting to get lost in the weeds a little bit here. So that would be somewhere around 0.1 on energy intensity. And yeah, the carbon would be way down here. But a point I surely would like to make is it's most certainly not a flexible grid resource, right? Nuclear power plant is about as binary as you can get. You have to turn it on or just turn it off. And to turn it back on, you actually need to discharge a compressed air energy storage to get enough power to get that turbine spinning again.
Suggest you call PG&E and ask them how Diablo Canyon works. If you really want to be honest about it, why don't you be honest?
Yeah, you in the far back.
Thanks for the research and thanks for your lecture. On the question of some other ones that are popping up as terms of either generation or storage, what made you choose to just focus on wind or PV? Did you sort of, in hindsight, want to kind of tinker into maybe, these, but I didn't want to put it in, or
Absolutely.
what do you see on
I really
that
want to
feature?
explore other grid flexibility options like demand-side management, smart grid technologies, and different resources. Why did I focus on this set? That's just the nature of research. So this is a set of 3 papers. And you ask questions, and then you get curious about other questions. But you've already collected so much data on different things that these questions begin to be formed based on the work you've already put in. Yeah, but it leaves plenty of work for everybody else to do some analysis as well.
So I thought, did you see anything into hydrogen fuel cells or anything about storage or
Talk
generation?
to Dr. Matthew Pello. I don't know where he is. Yeah, right there. He's done a lot of work on the life cycle energy cost of hydrogen fuel cells. Yes.
This was a really complicated but excellent talk, and I hope this will be online to review. You started the graph with a place where the U.S. energy is, that dot in the center of the quadrant.
Yeah.
Where would it be for other countries? Where would it be for countries in Africa, Canada, Europe? How different will it be? And basically my question is, how long does, you said it would take 35 years to maybe get this up and running in the United States? If I understood that. What would it take to get it up and running in the world? Time is of the essence with our carbon emissions.
I don't know, I'm just a physicist. That's an excellent question, though. But it is very different in different parts of the world. So I currently live in Bellingham, Washington, which is 30 miles south of Vancouver, BC, and their grid is comprised of 86% hydroelectric. And so they're already way down here. Sorry, I'll answer. Yeah.
The return on investment graph at the beginning with the, I think it was wind power. Do you know, they had like 8-to-1 return on investment. Do you know if that's subsidized cost or not subsidized cost?
That's not subsidized. So this was from fundamental life cycle assessment data of materials. It was not an economic input of output. No. Yes.
Why would you put lithium-ion car batteries? Put them close to lithium-ion stationary batteries? Or would you consider that they are financed anyway, bought anyway? Yeah.
Can you repeat that?
This starts getting kind of interesting, right? Like the embodied energy cost was already paid. So, oh, you're right. He asked, where would I put a lithium-ion car battery on this plot? So there's an idea presented by people at Tesla and among other places that once you can't go 0 to 60 in 2.4 seconds or whatever, then that battery could be used on the power grid. And so that's an excellent point. So yeah, that would be something an accountant would have to consider. How would you amortize the energy cost for the car versus amortizing the energy cost for the power grid? Yeah.
Looks like you've done it. Thanks again.
Thank you.